Welcome to the deep end. Today, we are dissecting the physics of distributed data. When you move past a single server, your safety net vanishes. Data fractures across boundaries, and the simple asset guarantees you had used to start breaking. I'm going to show you exactly how this fails in production, and more importantly, how we fix it. Before we dive in, please hit that like button, subscribe, and share this with your team. Also, check out our companion site, bitbytoken.com, for foundational deep dive and system design blueprints covering software, data, AI, and machine learning. So this is what the site looks like. The link is bitbytoken.com. I'll put the link in the description below. Do check it out. It is broken down into different components. So you can go to software engineering and similarly to other data engineering and AI. Within each of these engineering principles, we can go to fundamentals. You can search for any article, say indexing. Each of those topics are broken down further into basics, expert, and advanced. Actually, it's basic, advanced, and experts. And then we can also look at the various solutions which have been implemented. We have tried to make all the solutions quite extensive. We start with functional, non-functional requirements. We try to provide a detailed design using data model. Um, Along with data model, we try to provide details around the sequence diagrams. Further down, we provide scalability and availability pieces. Then there are certain trade-offs and consideration, which are very particularly important for your system design interviews in various tech companies. So yes, do take a look at this and provide us with your feedback on how we can make this site better. And if there are any other article that you would like us to put details up here. Now let's come back to this mechanics here. Okay, my next slide is, okay. First look at our baseline, the partition monolith. Everything shares one memory space and one transaction log. Query pruning is your best friend here, dropping 50-second queries down to 50 milliseconds. The key is that there are zero network hops. Your asset guarantees are enforced by local physics. This is safe, but it's not scalable. When we move to sharding, we cross the wire. We scale out, but the sharded log is gone. Or, my bad, it's a shared log is gone. Shards 0, 1, and 2 are now completely independent database instances. The network boundary is the most dangerous part of your architecture. This is where consistency guarantees goes to die if you aren't very careful. In a state of grace, we design our systems to keep writes on a single shard. You get microsecond latency, no external coordination, and absolute atomicity thanks to the local write ahead log. If a write fails, a simple local rollback undoes everything. This is the gold standard for distributed design. But then the fall from grace happens. The multi-partition write. Alice said Bob $200. Shard 1 commits, but then shard 3 dies mid-transaction. Now you have a partial commit, and you have no shared log to roll back shard 1. Your money is effectively lost. This is the nightmare scenario we have to architect against. Under the hood, we use the classic 1970s fix, the two-phase commit, or 2PC. Phase 1 is the prepare phase. We introduce a global coordinator who asks every involved shard, can you commit? The shard must lock their resources and wait. Nothing else can touch these rows. In phase 2, if and only if all shards vote yes, the coordinator pulls the trigger and broadcasts a commit. Atomicity is restored across the network boundary. If even one shard votes no, the coordinator sends an abort, 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 and everyone rolls back. It's reliable, but it's heavy. Here is a warning zone. The brutal cost of 2PC. Atomicity isn't a free lunch. You're doubling your latency with two full round trips, and you are causing massive contention because you're locking rows across continents. Plus, if a coordinator crashes during the freeze, your shards remain locked indefinitely. It's a massive performance tax. The modern alternative is the Saga pattern. We trade strong atomicity for availability. We break one big transaction into a series of local transactions across services. Each service reacts to events. We trade strong atomicity for availability. We hold no global locks, so the system remains lightning fast and highly available. But how do we handle failures in the Saga? We use compensating rollbacks. When a downstream step fails, we don't hold global locks. We simply run undo events in reverse. Just be aware of intermediate visibility. A user might briefly see a partial state before the compensation completes. We're fighting physics here. The cap and the pace LC algorithms or theorems. You cannot beat the law of networking. During a partition, you must choose between availability and consistency. Under a normal operations, you choose between latency and consistency. You need to pick the setting on this dial that matches your business needs. This is the masterclass in partition key design. The best multi-partition write is the one that never happens. We use co-location to keep related data together, but watch out for the hot shot, like an e-commerce site crashing on the November node during a Black Friday. Sometimes you just can't avoid a cross-shard split. Look at how the industry giant manage this physics. Google Spanner pays the latency tax and uses atomic locks to ensure global external consistency. Correctness trumps speed. Amazon DynamoDB, however, defaults to speed, using asynchronous multiplication to keep everything snappy. There are two different answers to the same problem. Consistency isn't binary, it's a spectrum. You have eventual consistency for speed, snapshot, and serializable for moderate protection, and linearizable for the highest possible consistency. Each step to the right gets exponentially more expensive. Tune this knob carefully. To wrap up, here is the senior engineer decision tree. To master your partition keys is to minimize cross-shard work. Guard your performance by using 2PC only when strictly mandated, and always accept eventual consistency where the business allows it. If you can articulate these trade-offs in an interview, you're the one who gets the offer. What's the most difficult scaling trade-off you have had to make? Let me know in the comments below. Again, do check out our site bitbytoken.com. Link again is in the description below, and share your feedback with us. Don't forget to like, share, and subscribe, and I'll see you in the next one.